Steps in hypothesis testing, traditional method. Let's go ahead and get right into your student notes. Keep in mind that this section contains lots and lots of definitions, and pay close attention to the definitions at hand. They will be helpful for the rest of this chapter and the rest of the semester. First, let's look at a preview to hypothesis testing. Researchers are interested in answering many types of questions. These questions are stated as claims about a population, and the decision-making process for evaluating these claims is called hypothesis testing. Researchers define the population under study, state the hypothesis or claim to be investigated, set the significance level, select a sample from the population, collect the data, run the statistical test, and reach a conclusion. We will consider three methods of performing hypothesis tests. First, this section, the traditional method. Next, the p-value method. And finally, the confidence interval method. Let's take a look at the definition of statistical hypothesis. A statistical hypothesis is a conjecture about a population parameter. The conjecture may or may not be true. Keep in mind there are always two sides to a conjecture: the conjecture and its complement. Next definition is the null hypothesis. The null hypothesis, symbolized by H sub 0, is a statistical hypothesis that states there is no difference between a parameter and a specific value, or that there is no difference between two parameters. In contrast, we also have something known as an alternate hypothesis. The alternative hypothesis, symbolized by H sub 1, is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. Compare these two definitions. Keep in mind that the null hypothesis and the alternative hypothesis are frequently used together in any given research. The null hypothesis always states that the parameter is equal to a specific value or another parameter. The alternative indicates change. So the alternative hypothesis claims that the parameter is either not equal to, greater than, or less than a specific value or than another parameter. Let's take a look at an example. In particular here, we will be presented with several different examples, and we are asked to state both the null and alternative hypotheses for each example presented. First, let's look at the claim that the average age of first-year medical school students has decreased from 29 years. The researcher knows a previous value for the average age, but believes that the age has decreased. Thus, no change would mean that the age is the same as it was before. And so the null hypothesis is simply just the average age is still 29 years. In other words, H sub 0 would be mu equaling to 29. Since this researcher believes that the age has decreased from 29, the alternative hypothesis is that H sub 1 would be mu less than 29. Let's not forget that mu represents the mean. This test indicates that the only change of interest is less than 29. So this test is called a left-tailed test. Let's take a look at another example. The average number of seasons in which an NBA player participates is 4.71 seasons. Now here, the researcher is concerned with the number of seasons NBA players play. Has the number of seasons increased, decreased, or remained unchanged? A previous study indicates the average number of seasons for the population of NBA players. The hypotheses for this claim are as follows. The null hypothesis, once again, means there's no change, so the mean would stay at 4.71. But since the researcher does not indicate a claim of greater than or less than, the alternative hypothesis would simply be mu is not equal to 4.71. This test indicates that the change could be more or less than 4.71 seasons, so this is called a two-tailed test. Let's take a look at another example. The average number of monthly sessions on the internet by a person at home has increased from 36. The null hypothesis would be mu equals 36. Since we're saying it's increased from 36, the alternative hypothesis would be mu is greater than 36. The change of interest is an increase from 36. The test here would be called a right-tailed test. Next, the average cost of a basic cell phone plan is at least $79.95. Now, since at least means greater than or equal to, a change would mean that the cost would be less than $79.95. And so our null hypothesis would be $79.95, and our alternative hypothesis would be less than $79.95. This would be a left-tailed test. For this next one, I invite you to pause the video and try this on your own. Please state the null hypothesis and the alternative hypothesis, indicate what kind of test it is, and verify your results with mine. Here, I got a null hypothesis of 8.2 and an alternative hypothesis of mu is not equal to 8.2, meaning this is a two-tailed test. Here we see a table that summarizes two-tailed tests, right-tailed tests, and left-tailed tests. We'll revisit this later on in the semester, but for now, take a quick look and see if you agree. Keep in mind that the null hypothesis is always stated using the equal sign. This is very important. When researchers conduct a study, they are usually looking for evidence to support their claim. Thus, the claim should be stated as the alternative hypothesis. The alternative hypothesis is also called the research hypothesis. Keep in mind that a claim can be either the null or the alternative hypothesis. However, statistical evidence only supports the claim if it is the alternative hypothesis. Statistical evidence can be used to reject the claim if the claim is the null hypothesis. This last statement is very significant. Pause the video, read this last statement a few times, and make sure you understand it. After stating the hypothesis, the study is designed. The researcher selects the correct statistical test, chooses an appropriate significance level, and makes a plan for conducting the study. For example, in 8.1 Part E, the researcher selects a sample of patients who will exercise 30 minutes a day for 6 weeks. At the beginning and at the end again of the 6 weeks, the weights of the people are measured. I think you would agree that this would be an appropriate statistical test. Recall that for samples of a specific size randomly selected from a population, the means of the samples will vary about the population mean, and the distribution of the sample means for sample sizes of 30 or more will be approximately normal. Even if the weight loss from the previous example spoken of is exactly 8.2 pounds and the null hypothesis is true, the mean of the weight loss for the sample of people will not, in most cases, be exactly equal to the population mean of 8.2 pounds. So there are two possibilities of this outcome. Keep in mind, this is also applicable to other examples. That is to say, the null hypothesis is true if the difference between the population mean and the sample mean is due to chance. Or the null hypothesis is false and the sample came from a population whose mean weight loss is not 8.2 pounds, but is some other value that is unknown, especially if it's significantly different from the population mean. The larger the difference between the claimed population mean and the sample mean, the more evidence there is for rejecting the null hypothesis. The probability that the sample came from a population with a mean of 8.2 decreases as the distance between the means increases. Keep in mind that any decision for any example must be made statistically rather than based on feelings or intuition. The difference must be significant and most likely not due to chance. Here's another definition. A statistical test uses data obtained from a sample to make a decision about whether the null hypothesis should be rejected. Another definition is called the test statistic. The test value, or test statistic, is the numerical value obtained from a statistical test. Decisions made to reject or not to reject the null hypothesis on the basis of the test statistic obtained from a statistical test rely on data from a sample drawn from the population. If the difference between the sample mean and the population mean is deemed to be significant, the hypothesis is rejected. Otherwise, the null hypothesis is not rejected. Keep in mind too, though, that because sample data are used to decide to reject a null hypothesis or not, it is possible that an incorrect decision can be made. In reality, the null hypothesis may actually be true or may actually not be true. Regardless of actual truth, a decision to reject the null hypothesis or not is made. Thus, there are two possibilities for a correct decision and two possibilities for an incorrect decision. Here are the following possibilities. First, an incorrect decision is when we reject the null hypothesis when it's actually true. This is known as a type 1 error. A correct decision is when we reject the null hypothesis because it's a false hypothesis. Another correct decision is that we do not reject the null hypothesis, especially when it's true. And finally, an incorrect decision is that we do not reject the null hypothesis when it's actually false. This is known as a type 2 error. Note here, this table indicates the 4 total possibilities that may occur. In particular, look at the type 1 and type 2 errors. Those indicate the incorrect decisions that could possibly be made based on faulty research or an uncareful eye. Once again, a type 1 error is when a true null hypothesis is rejected, whereas a type 2 error is a false null hypothesis is not rejected. Let's go ahead and look at this example and identify the 4 possible decisions that could be made. A medical researcher is interested in finding out if a new medication changes the pulse rate of patients who take it. Suppose the mean pulse rate for the population under the study is 82 beats per minute. Then the null hypothesis is that there is no change in the patient's mean pulse rate from 82 beats per minute after taking the medication. That is to say, H sub 0 is mu equaling to 82. The alternative hypothesis is that the mean pulse rate for the patients after taking the medication is not 82 beats per minute. That is to say, H sub 1 gives us mu not equal to 82. Once again, as mentioned earlier, let's identify the decisions that would be correct and which ones would result in a type 1 or type 2 error. First, if the null hypothesis is in reality true, then it is a correct decision not to reject the null hypothesis. In other words, the mean pulse rate for the population of patients is 82 beats per minute, and the sample mean is not significantly different from 82 beats per minute. The researcher then believes that the medication does not change patients' pulse rates. The researcher, therefore, does not reject a true null and made a correct decision. The second decision that could be made: if the null hypothesis is in reality true, then it is an incorrect decision to reject the null hypothesis. This would be a type 1 error. In other words, the mean pulse rate for the population of patients is 82 beats per minute, and the sample mean is significantly different from 82 beats per minute. The researcher believes that the medication changes the patient's pulse rates. The researcher has rejected a true null hypothesis and made a type 1 error. Three, if the null hypothesis is in reality false, then it is a correct decision to reject this null hypothesis. In other words, the mean pulse rate for the population of patients is not really 82 beats per minute, but the sample mean is significantly different from the 82 beats per minute. Then the researcher believes that the medication changes patients' pulse rates. The researcher has rejected a false null and made a correct decision. And finally, if the null hypothesis is in reality false, then it would be an incorrect decision not to reject the null hypothesis. This is a type 2 error. In other words, the mean pulse rate for the population of patients is actually not 82 beats per minute, but the sample mean is not significantly different from 82 beats per minute. The researcher believes that the medication does not change patients' pulse rates. The researcher has not rejected a false null and made a type 2 error. Let's take a closer look at the null and alternative hypotheses. We first should keep in mind that researchers make decisions based on sample data. If the evidence against the null hypothesis is strong enough, the null hypothesis is rejected. If the evidence is weak, the null hypothesis is not rejected. Their decisions do not prove that the null hypothesis is true or false. Statistics, in fact, does not prove anything absolutely. The only way to prove anything statistically is to use an entire population, which is typically improbable or sometimes even impossible. Thus, it's important to decide how large the difference between the mean obtained from the sample and the hypothesized mean must be in order to decide whether to reject the null hypothesis or not to reject the null hypothesis. That leads us to the next definition, known as significance level. The level of significance, symbolized by the Greek letter alpha, is the maximum acceptable probability of making a type 1 error. That is to say, the probability of making a type 1 error will equal to alpha. Statisticians usually agree on using 3 arbitrary significance levels, that is 0.10, 0.05, and 0.01. Depending on the level of significance selected, if the null hypothesis is rejected, the probability of making a type 1 error is 10%, 5%, or 1%. Once a significance level is chosen, the corresponding critical value is selected from a table or appropriate test. If it's a z-test, we use a z-table. If it's a t-test, we use a t-table. This is very significant. Please do not take this lightly. The critical value is the value that separates critical regions from non-critical regions. Let's go ahead and define a critical region. The critical or rejection region is the range of test values that indicate there is a significant difference that the null hypothesis should be rejected. A non-critical region, or non-rejection region, is the range of test values that indicates the difference that was probably due to chance and that the null hypothesis should not be rejected. A critical value separates the critical region from the non-critical region. The symbol for critical value is CV. For an alternative hypothesis, say h sub 1 is mu is greater than 40, for example, that uses a greater than symbol, the null hypothesis will be rejected only when the sample has a mean that is significantly greater than 40. Thus, the critical value must be on the right side of the mean. Then the test is called a right-tailed test. For an alternative hypothesis, where mu is less than 40, that uses the less than symbol. The null hypothesis will be rejected only when the sample has a mean that is significantly less than 40. Thus, the critical value must be on the left side of the mean. Then the test is called a left-tailed test. A one-tailed test, as noted above, either being right or left, indicates that the null hypothesis should be rejected when the test value is in the critical region on one side of the mean. A one-tailed test is either a right-tailed test or a left-tailed test, depending on the direction of the inequality of the alternative hypothesis. To find the critical value, the researcher must choose a significance level called an alpha level. Remember, though, that alpha is the complement of the confidence level. So to find alpha, you must subtract the confidence level from 1. Suppose the medical researcher chose to use a 99% confidence level, and thus an alpha of 1 minus 0.99, or rather 0.01. If the alternative hypothesis is that the mean pulse rate is greater than 82 beats per minute, mu greater than 82, then the z-value is such that 1% of the area falls to the right and 99% of the area falls to the left. Using the table, find the area value in the body of the table closest to 99%, or 0.99. In this case, if you look at the table, it would be 0.9901. Pause the video to verify. Thus, the value of z would be 2.33. I recommend here that you pause the video, take a look at the table, and verify this is true. Also, let's take a look at the next slide, where you can see a picture where this would be true. Here, we're finding the critical value for when alpha is 0.01, being a right-tailed test. Once again, take a look at this stripped-down version of the table, where we can find 0.9901, working backwards to see that our z-value is 2.33. With your experience from previous sections, I'm sure that you would agree by now that z equals to 2.33 in this case. Now suppose the medical researcher chose an alternative hypothesis that the mean pulse rate is less than 82 beats per minute with mu less than 82. Then the z-value is such that 1% of the area falls to the left and 99% of the area falls to the right. This would be a left tail alternative hypothesis. Once again, using the table, we find the area value closest to 1%, or 0.01. In this case, it would be 0.0099. And as you'd probably imagine, the value of z is negative 2.33. And what if the research question was about whether or not the mean is different from a particular value? As in the case of an alternative hypothesis, that the mean pulse rate is not equal to 82 beats per minute. That is to say, mu is not equal 82. The researcher in this case would be conducting a two-tailed test, and the null hypothesis can be rejected when there is a significant difference above or below the mean. For a two-tailed test, the critical region is separated into two equal parts, each having an area of 1/2 of the alpha. For instance, when alpha is 0.01, then alpha over 2 is 0.005. And 0.005 is to the right of the mean, and 0.005 is to the left of the mean. The z-score to the left is found by looking up the z-score corresponding to the area of 0.005 on table E. 0.005 falls halfway between 0.0051 and 0.0049 on the table. The z-score in this case would be negative 2.575. Pause the video and see if you agree by looking at the table yourself. If the z-value is needed to 3 decimal places, or negative 0.258 if rounded to 2 decimal places. The value of the z-score on the right is opposite to the left-hand z-score, so due to symmetry, that means our right-hand score would be positive 2.575, or rounded to 2 decimals, 2.58. Here we can see these values reflected in a graph. This would be known again as a two-tailed test. Let's go ahead now and look for the steps for finding critical values for specific alpha values using the table. Step 1. First, we'll draw the figure, the normal curve, and indicate the appropriate area. You notice we've done this in the past. It is very helpful to have a visual before you move forward. First, if the test is left-tailed, the critical region with an area equal to alpha will be on the left side of the mean. If the test is right-tailed, the critical region with an area equal to alpha, then it will be on the right side of the mean. If it's two-tailed, then alpha must be divided by 2. 1/2 of the area will be to the right of the mean, 1/2 of the area will be to the left of the mean. Once this is established, go to step 2. For a left-tailed test, we use the z-value that corresponds to the area equivalent to alpha in the table. For a right-tailed test, we use the z-value that corresponds to the area equivalent to the complement, or that is 1 minus alpha. For a two-tailed test, we use the z-value that corresponds to alpha divided by 2 for the left value. It will be negative, of course. For the right value, we use the z-value that corresponds to the area equivalent to 1 minus alpha over 2, or use the opposite of the left value due to symmetry. This will be positive. Now let's look at the steps for hypothesis testing. The first step will be to state the null and alternative hypotheses, then identify the claim. We did this earlier with several examples in stating the null and the alternative hypotheses. Next will be to design the study, select the correct statistical test, choose a level of significance, define the population, determine how the sample is selected, and then decide the methods used to collect the data. Next will be to conduct the study and collect the data. After that, evaluate the data, tabulate the data, perform or conduct the statistical test, decide whether to reject or not reject the null hypothesis, and then finally summarize the results. Now let's take a look at the steps for solving hypothesis testing problems using the traditional method. First step starts in a similar fashion. State the hypotheses and identify the claim. Next, find the critical values from the appropriate table, whether it's z-test or t-test or whatnot. 3, compute the test value. 4, make the decision to reject or not reject the null hypothesis. And 5, summarize the results. This table can help you in deciding on whether or not to reject or not reject a null hypothesis. Statisticians only state that there is or is not enough evidence to conclude that a claim is probably true or false. Again, nothing is actually proven in statistics. And once again, the only way to prove that something would be true would be to use the entire population. And as I mentioned earlier, it is usually impossible or impractical to do this, especially when the population is quite large. Let's go ahead and take a look at another example. The Incredible Edible Egg Company recently found that eating eggs does not increase a person's blood serum cholesterol. 500 American adults participated in the study that lasted for 2 years. The participants were randomly assigned to either a no egg group or a moderate egg group. The blood serum cholesterol levels were checked at the beginning and at the end of the study. Overall, the group's levels were not significantly different. The company reminds us that eating eggs is healthy if done in moderation. Their claim is that many of the previous studies related to eggs and high blood serum cholesterol jumped to improper conclusions. Can they make this claim? Let's first answer the following questions. Why did the company conduct the study? The company wanted to show that moderate intake of eggs does not result in high blood serum cholesterol. Perhaps they did this out of self-interest for the company. Perhaps they did this honestly. But let us continue to address some more items. Next, we identify the population under study, which will be American adults. So what is the research hypothesis? Is it the null or the alternative hypothesis? The research hypothesis is that eating eggs in moderation does not increase a person's blood serum cholesterol. This is the null hypothesis. The alternative hypothesis states that eating eggs in moderation does increase the blood serum cholesterol. Was a sample collected? The article does not state how the participants were selected, only that the group was separated randomly into those eating eggs in moderation and those not eating eggs. Was data collected? If so, what data? Data certainly was collected. The blood serum cholesterol levels for each group were checked at the beginning and at the end of the study. Were statistical tests run? If so, were they left, right, or two-tailed tests? Statistical tests were definitely run, and they used right-tailed tests. What conclusion was drawn? The conclusion is that the group's levels were not significantly different, and that any differences that were found were due to chance. What might be the reason that the previous studies drew different conclusions? For this, the answers may vary, but what are your thoughts? Once again, this study was done by a company that actually sells eggs. Is it possible there's a conflict of interest? Is it possible that the study was done in an improper way or a proper way? It really matters on how the study was conducted. But once again, the answers here would vary. This example was an example of how hypothesis testing is set up and started. In future sections, we'll see how we can actually numerically draw a conclusion that can reject or not reject the null hypothesis. As we'll talk about in future sections, we also need to find out how to use the p-value in order to find whether or not to reject or not reject a null hypothesis. The p-value, or probability value, is the probability of getting a sample statistic, such as the sample mean, or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true.